Okay. Welcome everyone to our March LHS seminar series. I'm Salmia Mayapin. I'm the manager of the Learning Health System here at Women's College Hospital. And before I go ahead and introduce our speakers visiting from SickKids, I thought I'd just give a very quick kind of recap about our Learning Health System seminar series. So as many of you know, Women's is on the journey to becoming a learning health system. And this is a model where we will foster a culture of curiosity and engagement and really think about and reflect on whether what we're doing is adding value and where we can work together to affect improvements. This seminar series in particular was launched back in September, and it's essentially been running monthly. So we've been featuring a lot of external speakers. If you were able to join last month in February, you would have noticed we had a set of internal speakers as well to share their experiences. And of course, the whole purpose behind the series is to inspire ideas on what a learning health system could look like at Women's College, but also think about what are the different components we need to consider. And that's why we're very excited about today's presentation, to really think about data, accessing data, even machine learning, which I think is a topic that many of you are quite excited about. And of course, the seminar is open to everyone at Women's, so that includes all staff, trainees, and physicians. A very quick recap of kind of our calendar so far. So as you can see, we've held 5 sessions so far. We have 4 more to go in the season, including today's session. And just so everyone knows, these recordings to these sessions are available on our website, and we'd be happy to share the link in the chat as well. So without further ado, I'm going to go ahead and introduce our speakers for today. They will be speaking on the SickKids Data Sciences Unit Strategy to enable data use and machine learning. So we have a panel of 3 speakers, a team of 3 speakers, I should say, and starting with Dr. Lillian Sun, who is a professor as well as a pediatric oncologist and chief clinical data scientist at the Hospital for Sick Children. Dr. Sung has a clinical research program focused on improving supportive care for children with cancer and implementing machine learning. She holds a Tier 1 Canada Research Chair in Pediatric Oncology Supportive Care, and she's the principal investigator on multiple operating grants from the NIH, the Canadian Cancer Society Research Institute, and CIHR. Secondly, we have Dr. Adam Yan, who is an assistant professor and also a pediatric oncologist at SickKids. And Dr. Yan has completed postgraduate training in pediatrics, pediatric hematology oncology, and clinical informatics, and also has a clinical research program focused on the use of electronic health records to support patient safety and quality improvement work, as well as implementing machine learning for clinical use. And last but not least, we have Dr. Lynn Lawrence Guo, who is a machine learning specialist at SickKids, and he's involved in architecting and really building CEDAR, which you're going to hear more about in this talk. That's the SickKids enterprise-wide data in Azure repository. And he has a keen interest in the full life cycle of creating and deploying performance and robust machine learning modules to aid clinical decision making. So welcome to all 3 of you. I'm going to stop sharing my screen so that you can go ahead and start your presentation.
Thank you for that introduction. We're just going to share our slides. Yeah, thank you. Sorry, give us just a second. Great, perfect. Oops.
Great, looks good.
Get rid of the notes box or no? Make it small. Sorry, we're just fiddling with the settings. Great. Okay, perfect. Thank you. All right, so I'm going to start us off. I'm going to go back.  'If I can. All right, so I'm going to start us off. I'm going to go back. If I can. 'If 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 going back. Perfect. So sorry about that. I'm on a unfamiliar computer, so that's always a challenge. I'm Lillian Sung. I'm going to kick us off, and I'd like to start by expressing deep thanks to Sumia and Rulan for inviting us to present. And we're really excited to talk to you about the SickKids Data Sciences Unit strategy. So what we're going to cover today is a ubiquitous problem to all of us, which is challenges with data access. And we're going to describe our solution, which we've called the SickKids Enterprise-Wide Data in Azure Repository. I'll tell you about how we created it, and then talk about how we've used it to provide a de-identified data source in a common data model called OMOP, and to enable a new machine learning program called Predict. And then we will talk about some of the research we've done in foundation models for application to healthcare and end with some conclusions. So I'll start with the need for data in hospitals, which is ubiquitous. We need data for reporting purposes, both administrative and for administrative local use, for research projects and quality improvement projects, and finally, for machine learning. It's hard to do machine learning without data. And before I jump into that, I wanted to provide some context into SickKids. So SickKids is the largest tertiary care hospital in SickKids. And this slide provides some statistics about our size. So we have about 15,000 admissions per year, about 100,000 inpatient days, 290,000 ambulatory visits, and about 11,000 operating room procedures. And before I talk about data, it's probably useful to talk a little bit about our approach to the electronic health records at SickKids. Up until 2018, we used an Allscripts product. We called it KidCare. And then on June 2nd, 2018, we transitioned to Epic. And one of the unique things about Epic at SickKids is that we share our instance of Epic with another tertiary care children's hospital called Children's Hospital of Eastern Ontario. So we share one instance of Epic, these two large pediatric institutions. And I believe that Women's College is on Epic, but just to describe a little bit about how the data in Epic work is that all Epic instances or all Epic electronic health records have 3 associated databases. And it's sort of important to understand that because if you're trying to use the data in Epic, it's really helpful to understand how Epic stores data. The real-time data in Epic is stored in a database called Chronicles. This is not a relational database. It's a hierarchical database that's not suitable for general reporting. So to enable reporting, once a day, there is a transformation from that real-time data to a relational database called Clarity. But that database is very, very big. And that's actually the database that most data sciences programs like to use because it's the most direct translation from the real-time data. And then some institutions use another relational database called Caboodle, which is another transformation from Clarity that also occurs once a day. But most, as I said, most data sciences programs do focus on Clarity. So our experience at SickKids, and Rulan will know this better than most people, that data are very difficult to access throughout the institution. And why is that? All EHRs are complicated. Epic in particular is complicated. Clarity, you're used to your research databases. We're used to having one table of data, maybe 2, maybe 3. Clarity has 18,000 tables at SickKids. So just imagine that if you were trying to use that data, how you would manage that you would manage to find something if you had to sift through 18,000 tables. And what makes it more complicated is that one data element, like a lab test, will be distributed over many, many tables. And even that same data element, such as a lab result, may be in different tables depending on the workflow. So that just makes it really challenging to find any particular element. And timestamps are particularly difficult in Epic or Clarity because there are many, many timestamps associated with a single event, such as the time a lab test is ordered. There's probably going to be 10 or 15 different timestamps related to that ordering event. What that means is that when an Epic analyst goes to answer a reported query for a user, that initial query is usually incorrect. And that's because it's just so hard to get it right. And so what happens is that analyst does the query, gives it to the user looks at it and says, no, this is wrong, goes back to the analyst, this goes back and forth many, many times. And what that means is that any query often takes months to get correct with lots of iterations. And so you go through all that work and you think, great, I've now learned where that element is. Now, unfortunately, what happens is that knowledge is often lost with each new query. And that's because there's no way to save or easily save that knowledge. So what is CEDAR? So CEDAR stands for the SickKids Enterprise-Wide Data and Agitory. So the name says it all. This is a SickKids data source where we're really looking at data across the enterprise, and we have maintained it in the cloud or Microsoft Azure. And what we really mean it to be is a centralized source of curated data that we can now use across multiple purposes at SickKids. And the idea is that we understand and clean the data once, and then we use it ubiquitously. And we were able to publish our results this year. And Lawrence is the first author on that publication. So currently, the data in CEDAR mainly consists of the data in Epic. We also have the data in KidCare as well in CEDAR, but I won't really talk about that today. And what we've done is we're using that data to populate dashboards and to create reports, to cut data sets for requesters, such as research users. I'll talk a little bit about OMOP and why one might want to use data in a common data model. And then Adam and Lawrence will talk about machine learning. So why did we create CEDAR? So I have been trying to obtain data since I've been here at SickKids since 1998, and always been frustrated at our inability to access the data. And the idea is that our decisions really ought to be based on the best available data, whether those decisions are for administrative purposes or to answer research questions. And we believe that we can support data-driven decision-making by focusing on data curation and validation so that people are making decisions on high-quality data, and we can deliver that data quickly in hours rather than months. So this is how CEDAR works. So what I had mentioned to you is that Clarity is the main Epic database that most data sciences programs focus on. I'd mentioned that our Clarity includes both CHIO and SickKids data, which adds an initial complexity because we have an obligation to CHIO to strip out their patients if we're using the data for research or administrative purposes. So what we have done, I'll use this arrow, is that we have our Clarity database in a location that's shared between CHIO and SickKids. What we've done is we've made a copy of that Clarity database, and we have placed it in Microsoft Azure, and we update that data every night so that every morning we have a complete replica of the data in Azure. And the main reason we want a copy of Clarity is we don't want to interfere with hospital operations. This allows us to work with a copy of the data without worrying about interfering with regular daytime workflows. As I mentioned, currently about 18,000 tables. And what we've done is created stored procedures that run every night. So what I'm about to show you runs automatically. We don't do this manually. The first step in the pipeline is that we identified the tables that are important to us, And currently there are about 180 tables, but that's not a static number. That number will grow over time. And what we do is we maintain the structure of the clarity table, so the exact same column names, but all we're doing here is we're filtering out CHIO activities, encounters, and patients. So that now allows us to have a snapshot of the SickKids only data. Our next step in the transformation is then to transform that data to a structure that is easy to understand and easy to query. And we've called that the curated schema. And that's really our main source of data that we're using for creating queries, creating dashboards for machine learning. And that's what we're using to create our de-identified data source for research. From that curated schema, we make this de-identified data set for research in the OMOP Common Data Model, and that's only for research. So I'm going to talk about that a little later, but that's really a separate issue. Curated schema is what we're using to address reporting and most research needs. So this figure shows you the 18 tables that we have in curated schema. These are intuitively obvious, we think, to a clinician or most clinical researchers. There's a patient table, so 1 row per patient, hospital encounter tables, 1 row per encounter, a lab table, microbiology table, and so on. The lab table will have clinically relevant columns such as date time, well, the lab test, date time ordered, date time taken, date time result, what was that result value, the units, the reference range. So these are the structure of these curated schema tables. And one of the really important things we did in the creation of this curated schema is we understood that it would be difficult to do these queries from Epic. And we understood that there could easily be errors. There could easily be duplications. You could grab the wrong column, grab the wrong timestamp. And so what we did is we started with activities. And by an activity, I mean like a lab test or a medication administration. And we randomly sampled 100 activities. And we had data managers validate every column in those 100 activities. So for example, for a lab order date time, we made sure that that time was correct to the second. So if it was out by 2 minutes, it meant we were looking at the wrong column. So it meant that we had to figure out where was the correct column, and then we would redo the query. So once we had the activities validated for a particular table, we then randomly sampled encounters and patients to make sure that we didn't have duplications and that we didn't have omissions. And we did this for each of the 18 tables in curated schema. And each iteration or each table took about 5 to 16 iterations. So you can see that this is tens of thousands of validations that were done. But we thought this was a very, very important step because we really wanted our users to be confident that the data in CEDAR matched what they would see in Epic if they logged in as a user and looked up a particular patient. And that process took us about 13 months to complete. So with that process complete, we now have a validated curated schema that we can now use. And we began to use it for decision support. So decision support would address administrator needs in the hospital if they needed to know about activity in a specific unit. Health information management also required the data for submission to CIHI, for example, or the Canadian Institutes of Health Information. And so they began to use that data for their purposes. We also began to use CEDAR to meet requests for research cohorts. So if a researcher wanted a particular data set, we could give that to them. And we also use it to create OMOP, which is really a separate discussion. And then critically important, we now have this great source of data for machine learning. We can use the data not only to find outcomes such as mortality or vomiting or readmission as examples, but we can also use it for the predictors or features to train our model. So this slide just gives you just some examples of how we've been able to use CEDAR to meet some requests. So the first example in this top row, in 2022, just as we were completing the validation of CEDAR, there was this report of unexplained hepatitis in children worldwide. And this was gaining attention everywhere. So there was an urgent request made at SickKids to be able to understand our children at SickKids who had hepatitis, defined as an ALT/ST greater than 500, and understand something about these children. And so a request was made through the usual channels, and the requester was told that it would take months to get to that request and to do it. And so they turned to CEDAR and said, can you do that more quickly? And so we were able to complete this request in about a day rather than months. So we were able to very quickly, within maybe 30 minutes or 40 minutes, find all the children with an ALT or AST greater than 500 seen at SickKids since 2018, describe that prevalence, describe all the infectious positive cultures or tests done preceding or following that hepatitis event, and then look at outcomes. So look at admissions and intensive care unit visits and deaths. And as I said, we were able to do that very quickly, and we were able to conclude that hepatitis had not changed at SickKids over time, and certainly not due to the COVID pandemic. We've also been increasingly using CEDAR to meet reporting needs. And so, as you'll know, all hospitals need to submit data to CIHI around admissions, discharges, ED visits, surgeries as examples. And we have found that the current way that we understand that data had been incomplete, which is a problem when you're submitting data to a national organization. And we have been able to use CEDAR as the source of truth to define how many admissions are actually occurring at SickKids, how many ED visits are actually occurring. A few months ago, we became aware of a new Ministry of Health requirement for alternate levels of care. The current team that received that request did not know how to find that data. They asked us, our team, for help. And again, we were able to address that need within a couple of days. So very, very quickly. I'll then get into quality improvement. So we've been working with the Utilization Management or UMC committee at SickKids to begin to create some dashboards. The first dashboard we've created is an antibiotic utilization dashboard that I'll show you on the next slide. But we're increasingly showing dashboards such as laboratory testing utilization as well to try to improve our prescription and ordering practices. And finally, we've been able to meet the needs of the research community. So I think it's very important to start by saying people don't come to us with simple requests. People only come to us if they can't get the requests met in a usual fashion. And the first example I'd like to show you is with rheumatology flow sheets. So in EPIC, we place, at least at SickKids, a lot of our miscellaneous information, such as quality of life, but in addition to routine flow sheet data like vital signs within these flow sheet measurement areas. And so rheumatology indeed had created a whole bunch of flow sheets to be able to track their children with arthritis, as an example. And this included not only arthritis measurement values related to joints, but also some quality of life patient-reported outcome data. And they had wanted to be able to obtain all of their flow sheet data. When they came to us, the request had been waiting for over a year. So they came to us to see whether or not we could help them not only create an initial database of their rheumatology flow sheets, but then be able to repeat this over and over again. And we were able to meet that initial request in a few hours. So we were able to do that initial query. We then refined it to make sure it was quite complete. And now they have all of their flow sheets that we can easily update at any time because we have the whole curated schema structure. Another example is that a neurologist came to us and wanted to find all EEG reports with the term burst suppression in the reports. And again, that researcher had been unsuccessful in finding someone to meet those needs. That was easily accomplished, I think, in an hour. The third example was a researcher who wanted all voriconazole administrations, levels, and interactive medications, very easy to do. And finally, another group wanted all medications, prescriptions, and labs for a specific cohort. Again, relatively straightforward to do once you have this curated schema structure. This just shows the antibiotic stewardship dashboard that came from that UMC request. What this shows is antibiotic utilization in terms of days of therapy per 1,000 patient days, listed by unit and by service. And so they're able to use this dashboard for audit and feedback purposes, and also to meet some data or reporting needs to other organizations where they feed that data back to more central national and international organizations. And then the final area that I wanted to address is multi-center research. Many of you will do multi-center research or do work with multiple centers. How do we normally do that? Well, normally my team would abstract data, or we might request data from Epic. Then we would send data to one common person. We need data sharing agreements. We need to send data. We have to centrally collate. We need to do a bunch of cleaning. And really importantly, we call everything something different, so that even if we were to request a cut of data from Epic, the way we call acetaminophen will be different in our institution compared to another institution compared to another institution. So we would somehow need to map that acetaminophen means all the same things at our different centers. What if multiple centers had all their data in the same format, the same structure, and used a common vocabulary? You could then do analyses independently and then meta-analyze or synthesize those results. And then you wouldn't need to move any data. And indeed, that's the idea behind OMOP. So OMOP stands for the Observational Medical Outcomes Partnership Common Data Model. This comes from Odyssey, which is based out of Columbia University. And it standardizes the structure and vocabulary of data to facilitate collaborations around the world. So there are some estimates that 13% of the world's population have their data in some OMOP somewhere. This table shows you, or this figure shows you the different tables in OMOP. On the left-hand side, this shows you that there's a person table, there's a death table, there's a visit occurrence table. We can't change that. These are standardized in every OMOP version, and all the column names are also standardized. But what's really key to interoperability is the idea of the concept. The concept takes every medical entity and labels it with a standard concept ID. So, for example, doxorubicin or acetaminophen will have the same concept ID no matter where you are. That means that I could do a query and ask the question, how many boys have received doxorubicin between this year? I could write one query and apply it at any institution, and I should get the right answer. So at SickKids, we created our SKOMOP DID last year, or we completed it. We de-identified it, so all identifiers were replaced by random surrogates. All dates were shifted plus or minus 30 days, but were consistent within the individual, so those intervals would be true, and we did not allow free text for this version. There are 1.8 million patients in our SKOMOP DID, 2.5 million visits, 1 million diagnoses, and 132 million rows of measurements. So it's quite big. And it's currently lives in the SickKids High Performance Computing Center. The advantage of that allows users to use compute easily and to gain an access and an account. It is available for anyone at SickKids with a researcher QI approval. There is no cost to users to do this, even for lots of compute, there's no cost. And we're beginning to do multi-center research now with Stanford, Columbia, and St. Justine. So it's pretty exciting to see this work start. And this is my last slide, just to say the one part I didn't show you of the CEDAR pipeline is this top right-hand corner. So this top right-hand corner, we realized that if we wanted to do machine learning, we also needed to bring in the real-time data. So what we have done is enabled a feed from the real-time database Chronicles in the format of HL7. And that HL7 messages are now coming into CEDAR in the same structure as curated schema, so that we can now easily merge those tables and have real-time data for the purposes of machine learning. And with that, I will hand this over to Adam.
Thanks, Lillian. I'm really excited to introduce everyone here to Predict. Predict is a new clinically oriented machine learning group at SickKids, and our goal is really to bring machine learning to the bedside to improve care for our patients and improve the experience for our providers. This is a basic outline of what the machine learning life cycle looks like. So we'll start at the top center circle. So first, what we do is we take all of the data that we have in CEDAR or in Epic, so going all the way back to 2018 when we went live with Epic, and taking whatever problem that we've been tasked with, we develop a model using our historic data that we have. We'll talk about what our benchmarks for success are in that process, but if we meet those benchmarks, we then move on to deploy that model in a silent trial. So during our silent trial, we're using real patient data in real time to make predictions, but clinicians are blinded to those predictions. This allows us to test how the model performs in the actual environment that it will be deployed in eventually. Again, if we meet some benchmarks of success in our silent trial, we integrate that model into the clinical workflow and turn it on into a live mode where clinicians actually receive these predictions and are able to alter their care for their patients based on that information. And once the model is live, we continue to monitor its performance and tweak aspects of it based on the feedback that we receive. So how do we develop a retrospective model? So the first piece is finding a problem that is well suited to machine learning. And while that sounds like an obvious first step, some might argue that this is actually the most difficult part of machine learning, finding what problem is well suited to machine learning. And we'll go through what we think is an appropriate framework for machine learning. So to identify a problem that we think we can meaningfully deploy a machine learning solution for, we evaluate both the healthcare team context and the clinical context of the suggested problem. So what does that mean? In terms of the clinical context, we can divide it into three sort of phases. The first is picking an outcome. So when a group comes to us with an idea for a machine learning project, the metrics that we look at are, is this problem clinically important? Is this something that is affecting patient care, operations, efficiency? The second thing is this relatively common? We appreciate that both at SickKids and at Women's College Hospital, a lot of us deal with niche areas of medicine. So our framework for what is common is somewhat flexible, but something that we see at least somewhat frequently. And then the third piece is that it's measurable in the electronic health record, or EHR. we need to find a data point in Epic that we can hang our hat on to say that this represents the outcome of interest. The next phase is we build our model. And we don't expect clinicians to be involved in the building a model phase. What we ask is that you have some reasonable expectation that using your clinical knowledge, that you feel that EHR data would have the ability to predict the outcome of interest. Finally, when implementing the model, we have two criteria. The first is that knowing the model's prediction would change clinical care. We don't want to provide clinicians with predictions or machine learning outcomes that are nice to know, something that they are interested in knowing, but not something that would actually change their behavior. So we ask all clinicians to articulate what would be their plan for a positive label or positive outcome, and what would be your plan for a negative outcome or negative prediction. And beyond that, we want to explore what would be the difference in care and outcomes that would occur based on that differential care provided on those predictions. So if all of these aspects are met, we feel that the clinical context is reasonable to move forward with potentially developing a machine learning solution to the articulated problem. But there's more than that. We know that when we implement a machine learning model, many excellent models that perform extremely well in situ are not implemented in an effective way. And that's because machine learning implementation relies on the clinical team to accept and adopt that framework. So for every problem, we identify a clinical champion from that group that is passionate about the problem and willing to lead that program. And the second piece is we ask that that person survey their peers and be able to articulate that their clinical team would be receptive to receiving that information. Because we don't want to provide predictions to people that they don't trust and don't feel that they would be able to use in their clinical care. So this is one example that we've been working on, and that is in terms of vomiting for pediatric cancer patients. We know that vomiting has a negative impact on quality of life for children with cancer. We also know that we can prevent vomiting by changing a patient's antiemetics. In an evaluation of our data at SickKids, we identified that 27, almost a quarter of our patients who are receiving chemotherapy as an inpatient vomit within 96 hours of admission to hospital. So our goal was to predict which oncology patients are going to vomit, and this would allow us to intervene earlier to change their antiemetics and hopefully prevent vomiting. So when we go back to our initially proposed use case criteria, is vomiting a good machine learning use case? Is the outcome clinically important? Yes, we know that vomiting has a negative impact on quality of life. Is the outcome relatively common? Yes, we know that more than a quarter of patients are going to vomit within 96 hours. Is the outcome measurable in the EHR? So we know that for our inpatients receiving chemotherapy, our nurses reliably chart vomiting. We know that for an outpatient receiving chemotherapy, we have no way of charting if they vomited or not. So we decided to limit this model to the inpatient setting. Is there an expectation that EHR data can predict the outcome? Yes, there are many known risk factors for vomiting, such as chemotherapy, toxicities, that we would believe that we could reliably predict this. Would knowing the model's prediction change clinical care? Yes, we know that there are different antiemetics that we can prescribe to change what we do for that patient. And do we believe that that change or differential clinical care would improve an outcome? Yes, I believe that if I change the antiemetics for my patient, there is the potential to reduce the risk of vomiting. Next, we talk about the clinical team context. So while Lillian and myself are both pediatric oncologists, this is not our project per se. We identified clinical champions from the oncology group, some pharmacists with expertise in preventing vomiting to champion this project. And through informal survey of our colleagues, we identified that the teams would be receptive to receiving risk stratification information. So vomiting met all our criteria to proceed with developing a machine learning model. The next piece is selecting a prediction time and a prediction window. So this allows us to understand when we want the predictions and when we want that data. Important things to consider are, how does this change for an inpatient or an outpatient? Who will receive the predictions? And is someone available at that time to actually receive the prediction and intervene on that? So the prediction time is the time the prediction is actually made at. And the prediction window is the time period in which the outcome we're trying to predict can occur in. So coming back to our vomiting example, we know that the highest risk period for vomiting is within the first 96 hours of admission. So we choose our prediction window to be 96 hours. We know that this will not account for all episodes of vomiting, but it accounts for the majority of episodes of vomiting. Next, we know that teams round at about 9 a.m. in the morning. So we felt that having a prediction time at 8:30 in the morning would allow us to have a significant amount of data to make accurate predictions, but still allow a buffer window to provide clinicians with this data with time to incorporate this information into their morning routines and use this data to make decisions on rounds at 9 a.m. So what does success look like? We believe that before you make a model, you need to set your benchmark for success. What is the goal for your model to obtain in terms of predictive abilities? And our benchmarks are really the minimum performance that we feel would be acceptable for clinical use. While there are many metrics that you'll read about in papers that evaluate how a model performs, we really want to focus on clinically interpretable metrics that clinicians can understand to have faith in the model. And we feel that the most clinically interpretable metrics are false positive and false negative rates. So for each of our models, we go through an exercise with end users to understand what false positive and false negative rate would be appropriate for them to have faith and to use this model. So once we've identified our problem of interest, our next step is to build features or predictors in that model. And what's very different about the machine learning work that we do compared to traditional research is that we're using all of a patient's historic data in Epic. So while for many research projects that many of us have done before, we might use 20, 30, maybe we're really novel and we're using 50 features, here we're using hundreds of thousands of features for each patient as predictors in our model. So really a large volume of data is going into each predictor. Once we've identified our predictors, we split our data. We know that we need to train our model on data and then test our model on a separate set of data that has been held out. And there are different ways that you can split data. One way is a temporal split, where we do our training on the earlier data. So in the figure below, from 2018 to 2022, we might use that data to train. And then we test our model on the more contemporary data from 2022 to 2023. An alternative way to split data would be to randomly split it. So use data points from across the time period for both the train and test sets. Next, we go on to train our model, and we use different model architecture, meaning that we will try different models. There's not just one approach to machine learning. So we might train and test numerous models for a different clinical problem and see which model performs the best. And choosing a model might vary based on what our objective is. Are we predicting a continuous outcome, or are we predicting a yes, no? After we've trained our model, we then validate it in another process as well. So finally, once we've trained and developed our model, we evaluate that model. So I alluded to earlier that we ask clinicians to a priori set model thresholds that they feel would be appropriate for implementation. So we look at what those existing thresholds are. We also go beyond that in our evaluation. We look at existing baselines. So are there other people who have evaluated predictions? Maybe that's even clinical gestalt or other non-machine learning based algorithms. and see if our model exceeds or meets those thresholds. And then we look at other metrics of our model as well. A really important area that has gained a lot of attention in machine learning is that of fairness. So in our models, we also will perform subgroup analysis. So we might look at how the model performs in different age groups, or look at how the model performs between men and women to ensure that the model is performing fairly for people with different attributes. Once in our retrospective study, we have developed a model that meets acceptable thresholds, we can move on to deploy that model in a silent trial. So this schematic has a lot of pieces because a silent trial is a complex process. But the one part I really want to draw attention to is the end users in the bottom right and this dotted red line with the X through it. What's really important is in a silent trial, end users are blinded from the predictions. And this is because we have not yet validated that our machine learning model works in real time on prospective data. And so we don't want end users to be using that information in their clinical care of patients. So during a silent trial, end users are blinded from the predictions, and the algorithm monitoring team, so our group at Predict, monitors the performance of that algorithm. And once enough predictions have been made, we're able to reevaluate the performance of that algorithm and work with clinical end users to determine if we should turn the model on and put it live so that clinicians are able to see those predictions. In terms of what we look at during the silent trial evaluation, first we look at data set drift or shift, sorry. We know that training data may be different than live data. A huge example of this was we know that during the COVID-19 pandemic, many models fell apart because we had a new variable that was introduced into these models that was not accounted for in the training data. So during data set shift, we can evaluate how the model performs compared to the training data. In terms of model performance drift, we can look at how the model's performance metrics compare to that of our retrospective analysis. And this allows us to understand how frequently do we need to be monitoring the model, how frequently do we need to update the model, and how long should our prospective trial last. And finally, we look at system performance. Many of us have tried to, log into Epic or the computer and we wait 10, 20, 30 seconds to log in. We want to understand how our machine learning models impact system performance, both on a user level and on the system level as well. So once we have gone through the silent trial evaluation, we're able to integrate our model into the clinical workflow. So here the end users are now provided with reports and data related to their predictions. And we really feel that integration into the clinical workflow is a key piece of the machine learning pie. So we really work with end users to develop clinical pathways where they articulate how they will handle a prediction and what they will do differently. And we provide end users with context around their predictions as well. So for vomiting, we don't just provide a yes/no binary outcome, will the patient vomit, but we're also working to provide end users with data around that prediction, such as what chemotherapy is the patient receiving, what antiemetics is the patient receiving as well. So in summary, we believe that a good machine learning model starts with a well-defined problem, quality data, and a good understanding of how that data is generated. We believe that developing a model for deployment requires additional considerations, such as the deployment environment, and that once we've deployed that model, there's significant ongoing requirements for learning, such as in a learning health system, to monitor how that model is integrated. I'm now going to pass on to Lawrence.
Thanks very much. And I'm so sorry to interrupt. I'm just keeping an eye on the time. It's about 12:51. And we would like to entertain any questions as well. But please go ahead.
Okay, sounds good. No worries. I'll try to make my part of the talk as short as possible. And my part of the talk really discusses some of the recent research work we've been doing. So since the release of ChatGPT a little over a year ago, there has been an explosion of increasingly powerful AI applications. So we have Google's Gemini, OpenAI's ChatGPT, and image generators like Midjourney and DALL-E that have really transformed the way we interact with technology. Under the hood of these AI applications are foundation models. And these are large AI models that are trained on vast data sets at scale using self-supervised learning. And the scale of these models and the data sets are what really gave these foundation models their impressive capabilities. And it's the learning technique or self-supervised learning that allows these models to learn at such large scale. As an example, the GPT language model that powers ChatGPT was trained to predict the next word in a sentence. And by doing so, it learns the structure of language. And so it can understand language and generate contextually relevant text. Once trained, you can really start to build lots of very useful interfaces like chatbots on top of these foundation models, or specialized models that are very useful for very specific use cases, like building a search engine. So in healthcare, a particular useful type of foundation model is known as Foundation Model for Structured EMR, or FEMR in short. And basically, these models can summarize the entire patient medical history up to any point in time using their data in the EHR. So we have, for example, patient medical history in the EHR, and how FEMR works is by formulating this medical history into a sequence of time-stamped code. So a prescription is basically a RX norm code with a timestamp. A lab is a LOINC code, sometimes with a value attached to it and a timestamp. And the diagnosis is an ICD code, the timestamp. You can think of this sequence of timestamped codes as the language of EMR. And with this formulation, you can train a foundation model using a similar approach as large language models like GPT, but instead of predicting the next word in the sentence, here we're predicting the next stamped code, time-stamped code in a sequence of time-stamped codes. And basically what this allows us to do once the model is pre-trained is to leverage the learned structure from the EHR by the foundation model and use it to summarize the entire patient history into a set of features, like Adam was mentioned earlier on. But the difference here is that these features are a lot more informative, and they're highly reusable to train any number of downstream prediction models. So how well do FEMRs perform? So we spent the last year or so evaluating foundation models in various different clinical settings in which traditional machine learning models fail. And one setting is changes over time. So models typically, in terms of their performance, start to decay over time due to changes in the patient population or clinical care practice. Here, for example, we trained models on data collected between 2009 to 2012 to predict whether a hospital admission would last for more than 7 days, or whether the patient would transfer to an intensive care unit during the admission. When we evaluate these traditional machine learning models here in black, we see that their performance started to decay as early as 2013 to 2016, and even worse in 2017 to 2021. Comparatively, for foundation models here in blue, not only do they perform better overall, they also demonstrate less performance decay over time. So what this means is that foundation models can really sustain their benefits longer than traditional machine learning models. Another setting is, or a challenge is that models trained in one population often perform not as well in another population. So here, for example, we trained models on the pediatrics population across 11 different tasks. We also trained the foundation model on only adults and adapted the models to perform predictions for the same 11 tasks. And when we evaluate these models on the pediatrics population, we see that the foundation model trained in adults performed significantly better than traditional models trained on pediatrics. And so what this means is that, for even specialized or smaller populations, we can still leverage the learned structure within these foundation models that are trained on a much broader and general population. So the caveat with the previous studies, which were published last year, is that they were all done in the same institution. And so next, we looked at the portability of these foundation models across hospitals. Traditionally, with model development, like Adam mentioned earlier, we start with a source EHR database, we extract a cohort, then we split a cohort into training, validation, test sets, then we go through an extensive feature extraction, curating hundreds of thousands of features, and this is very time intensive. And finally, we train task-specific models on top of these features. What we also did in this study is taking a foundation model that was trained on the patients from Stanford Medicine and use this foundation model out of the box to generate patient features for a cohort extracted from SickKids, and use these features to train prediction models for the same set of tasks. We also continued to train this foundation model on SickKids EHR in order for it to capture local data heterogeneity and also use it to generate features and use these features to train prediction models. What we see is that compared to the traditional models that we built directly on SickKids, a foundation model that was trained on Stanford Medicine out of the box performed competitively. And with continued training, it performed significantly better than the models trained directly on SickKids patients. So the benefits didn't end there. We also know that foundation models perform really well when there are few training examples. So what we also did in the study is that we reduced the number of training examples down to as little as 2 and increased it by a factor of 2 all the way up to 1,024. And here at 256 examples, it represents just 1% of the original training data. So what we see with the traditional models is that they failed miserably when we have very few training examples and their performance started to improve over time. But with a foundation model, even out of the box, it performs substantially better. And with continued training of this foundation model on SickKids data, with as little as 128 examples or less than 1% of the total training data, it performed as well as the traditional model trained on all training data available.
So we are at time. Do you have a wrap-up slide by any chance?
Yep, this is it. So this, to summarize, this really points towards a paradigm shift going from the traditional machine learning to sharing foundation models across institutions. It's also about sharing how to properly adapt these foundation models and offer eventually machine learning as a service for these much larger scale foundation models. And for concluding remarks, I'll pass it back to you.
So my apologies for the time. I think I spoke too long, but just to say that we want to thank a lot of people for all the work that we have shown you today, including from IMT at SickKids, the Data Sciences Unit, Microsoft, and DSI. So just to thank you for allowing us to present.
Thank you so much for coming to Lillian, Adam, Lawrence. We really appreciate it. It just means we'll have to bring you back for another conversation. And I'm sure folks have questions. Please feel free. We'll be sharing the link to the recording, but also please feel free to reach out to me. But you should be able to find the team's contact as well to pass along your questions. Thank you so much. And Lillian, Adam, and Lawrence, we will see you in the post-seminar chat. It's a separate Zoom link, so we will see you there shortly. Thanks everyone for joining. Take care.